We will, as we announced, talk about IEC 62353 compliant electrical safety testing for patient monitors today. And tomorrow morning, or tomorrow at the same time, we will have the same discussion, but about ventilators. So with patient monitors in mind, the IEC 62353 is part of the worldwide standards for minimum performance and safety testing. In the 62353 is the electrical safety standard that applies to doing electrical safety testing once the medical device has reached the hospital or medical facility and will be put into their inventory. So prior to that, in the manufacturer, for design validation or for final assembly testing on the factory floor before the medical device is shipped to the hospital, IEC 60601-1 is the more appropriate standard for them to use. Today, we're going to focus all our attention on IEC 62353 and how it is used when we're doing patient monitor testing. I'll remind you that the test load, which is what you see in the slide here, is the one in the international standards, and it's the same one that we use in our United States local national standards, which have been harmonized. As I said, 62353 is used in working locations outside of the R&D lab. So your biomed department, if you're doing testing inside the department, is certainly your lab, but it's not for research and development. It's not for designs. It's for doing the testing of medical devices that are already finished goods. They're ready to use, and they need to be tested initially when you receive the medical device. When you get it back, if you have sent it somewhere else to be repaired, you should repeat the testing. And then, of course, scheduled testing, which would be our periodic testing, is designed to be used for field service engineers of all kinds, from the manufacturer for sure, but also third-party biomedical service providers, as well as employees of hospitals and other medical facilities. IEC 62353 is not just, is the standard, but it doesn't have just one testing method and workflow or flow and sequence of tests like the IEC 60601-1 does. IEC 62353 has 3 different test methods, and you have to choose which one you're going to use. Now, when do you choose that? You make that choice the first time that you do electrical safety testing, when you receive a new medical device that you've never had before in the hospital, a new brand or model of that medical device. And then you choose a method, direct, alternative, or differential, from the standard that is appropriate for use for that category of medical device. Now, as I said, you do that at your incoming inspection, your acceptance test, and then you stick with that decision about which test method. So if I pick direct when I get this new medical device, this new patient monitor, then ever after that, I have to continue to use the direct method. I don't choose direct one time and then the next year when I do the testing again, choose a different. No, 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 no. You pick the method you're going to use when you add that medical device into your inventory at incoming inspection, also called acceptance testing. Today, we're going to focus our attention and use the direct method, and here's why. The direct method, unless there are other important reasons for picking a different testing method, is the most correlatable, the most like the IEC 60601-1. So if you're a field service engineer and I am the quality manager from the manufacturer of the medical device that you work for, I will tell you that I want you to use the direct method so that I can compare the results, the test results that you get when you do your testing back to the test results that we got in the final assembly test in the factory and also during the design validation testing that was done in engineering and R&D. So the direct method is the most correlatable. It's the one that is the most closely like the 60601-1. We'll see when and why we would pick alternative or differential in a minute. Another thing to remember about IEC 62353 is that the test current used for doing the protective earth or ground resistance test is only required to be 200 milliamperes, whereas in the IEC 60601-1, we require 25 amperes of current flow. Now, this doesn't mean you must only use 200 milliamps. You're allowed to use 200 milliamps or 25 amps, but whatever you choose, stick with it. Now, the test instrument that we're going to show you today, the ESA 615 electrical safety analyzer, can only do 200 milliamperes of testing. So we're going to do this testing today as if we were using the ESA 615 and we were doing it the way you would be using it in your biomedical department or in your field service organization. So a little bit more about how would we describe each of the test methods in the IEC 62353. In the direct method, the device under test is powered, and that means you turn it on, and the leakage currents are measured from all accessible parts, all patient connections that are continuously conductive from the medical device to where they touch the patient, and the applied parts with interruption of the protective ground. That means that we are going to do all of the tests and including the single fault test, at least the one about interrupting ground, and then looking to see how much leakage current is flowing and where it's flowing in terms of the other return paths. So we will be doing single fault testing along with the rest of the tests that we will do under direct method. The power supply is then inverted, meaning we reverse the polarity, and that means we would say to ourselves, what happens if L1 and L2 are connected backwards? They are not connected where they're supposed to be. They've somehow been cross-connected. We will reverse the polarity, therefore, and we will do the testing again in reverse polarity. So that's what happens in the direct method. In the alternative method, the power supply poles are short-circuited to create the same voltage between L1 and L2, and either the parts are connected or disconnected from the protection circuit, so ground would be lifted. In this situation, isolations are strained at a double voltage or better with the same voltage in both polarities. So we don't want to do this on every medical device, only certain medical devices, because we'll be comparing to what they are subjected to in case the device is normally powered. In the differential method, we would use a toroid transformer transversed by all of the active conductors of the power supply circuit of the electromedical device or system. The toroid gives a signal proportional to the differential current flowing through it. Now, does that mean you have to go out and buy a toroid? No, 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 no. Not when you use Fluke Biomedical test instruments. All of our electrical safety analyzers, when we're using the 62353 differential method, already take into account that toroid. It's built in. So you don't have to worry about that. So how will we make the choice then among these three testing methods that are available? Before we go to that though, here's a bit of a knowledge check. And we will open you'll see an opportunity for you to respond in a minute in the webinar. What are the three testing methods described in the IEC 62353? A, direct differential alternative. B, power on, power off, normal condition and reverse condition. Or C, normal condition, single fault open neutral, and single fault open ground. What is your choice about what you've learned so far?
Great, I'll go ahead and launch this poll. We'll give you guys a little while to answer this. All right, we'll give you guys about 20 more seconds to answer this. Looks like people are paying attention, Jerry. So
yeah, it's good.
they're doing a good job here.
Stay focused, my friends. There'll be more questions as we go.
I'm going to go ahead and close the poll and share it. So we have 87%, Jerry.
All right.
Differential and alternative.
All right, well, are we ready to see what the correct answer is? And here's the reveal. Indeed, it should be A, direct, differential, and alternative. Good job, good job. All right, let's continue then and learn a little bit more. In the IEC 62353, and I'm really sorry that this is very, very small. It doesn't work very well fitting on the slide. This is indeed in the IEC 62353 standard itself. There is this decision tree about how we choose the testing method that we will be using. So the first decision point here is it a class 1 device or some other classification? And if the answer is yes, then we follow down where it says yes. And the second question is about protective earth testing, I believe. So if the device that we're testing is not a class 1, now class 1 typically means that there are three connections on the power cord. L1, which is our hot wire, L2, which should be our neutral wire, and some means of ground. Now in the United States, we have 3 prongs on the plug end. In Europe, the EU power plug for 240 volts AC doesn't have a third prong for the ground, but it has a ground connection that makes connection with another metal piece on the mains power. All right, so typically it would have 3 connections on the power cord, and it will have typically an accessible ground, a ground test point that is usually on the back, but not always, on the back of the device, but not always. Sometimes it's somewhere else, but there will be an accessible ground. Now, there are newer medical devices that are called electrical safety class 1 that do not have this accessible ground test point. And so just to let you know, there's another webinar that we have done that explains what to do when you don't have that accessible ground, even though it's supposed to be a class 1 device. If the device is a class 2 or a class IP, then there's a different decision tree, but actually it turns out to be pretty much the same as what we're going to go through, and you'll make some decisions about what testing needs to be done or not done. Let me just see if there's anything else I need to cover here. All right, so that's our first decision point. And from there, we get to our first checkpoint, which is, does the device under test have a power switch? There are medical devices that do not have a power switch. They are turned on as soon as you plug it into mains power. That would be an example of a medical device that does not have a power switch. If it does not have a power switch, then we will move where it says no power switch, and we'll come down this decision tree. But we'll get there in a minute. If the device that we're testing does indeed have a power switch, then the answer is yes, and we'll proceed down, straight down on the decision. So if it does not have a power switch, meaning that it's live and powered on as soon as you plug it into mains, then we have to use the alternative method for testing. No choice, we have to use it. And the alternative method, as long as the leakage current is below 1 milliampere, and in a polyphase, meaning single or more than single phase equipment, will, in that case, will follow the table in the 62353 second edition. All right, no power switch, alternative method. Second checkpoint is the device under test isolated from protective earth or ground? Now, in some countries, the language doesn't have a separate word for isolated or insulated, but I need you to understand they are two very different things. Isolation means that there is a barrier of some kind where the electrical current flowing inside the medical device is not referenced to ground. It is referenced to something other than protective earth. And that's done to protect the patient from electrical short circuits and so forth, or high energy coming in that might come in through the ECG electrodes. So if the device is isolated, you will know that because the patient connections will be an F-type connection, meaning floating or isolated. They will be BF, which is body isolated, or CF, which is isolated for those kinds of patient connections that go directly inside the patient body and typically inside the heart itself. So it's really important. You will know because the medical device manufacturer will disclose that the device is isolated either through markings or symbols on the outside of the device, and certainly in the service manual or test procedures for the medical device that we're testing. So if again, we have a decision point here, is it isolated, yes or no? All right. So if it is isolated, then we get to choose either the differential or the direct method. It's up to us. As I said, if you're working for a medical device manufacturer in the field service organization, the quality manager should be requiring that the direct method be used. However, they may or they may not be. So that's the second checkpoint. Again, we're making a decision now about which testing method are we going to use to be compliant with the IEC 62353. If the device under test is not isolated from protective earth or ground, then we are required to use the differential method. Okay. If it is not isolated, we will use the differential method unless otherwise directed. Okay. So if there is no on-off switch, we use alternative. If the device is not isolated from ground, we will use differential method. If the device is isolated from ground, then we have a choice. We can use either the direct or the differential method. Okay. And the reason we would pick direct method is because it is the most like, the test results will be the most like what was the results that were gotten using IEC 60601-1 in the factory and final assembly testing, or in the design validation testing before, as the medical device was proven to be safe and effective for clinical use. All right, so those are our big decision points about which method. Note that all of the methods come back together here when we talk about patient connections, patient applied parts. These things are the connections to the patient that are continuously conductive from the medical device all the way to where they touch the patient. And there is no, there isn't any break in that. So let's move on and see what happens there. All right, so another little poll question here. Which test method? The medical device to be tested is classified as a class 1 device. It has an accessible protective earth test point. It has a power plug with L1, L2, and protective earth. It is powered on using a switch. The device includes F-type patient connections. And which IEC 62353 test method should you use? A, differential, B, direct, or C, alternative? Dan?
All right, I'll go ahead and launch this poll. We'll give you guys about a minute to answer this. All right, we're 50% is voted. We'll give you guys a few more seconds here. This one's a little more split, Jerry.
Mm-hmm. Well, remember, we did have a choice as part of what we just went through. So we're going to have an answer, but then we're going to also go back and do a little quick review.
All right, we have about 5 seconds and I'll close it. Okay, and we'll go ahead and share what the folks had to say. So 52% direct, 31% of them differential, and 16 alternative.
Okay. So here's the big reveal. The answer here we've chose is direct, and the reason is because we want the most the test results to be most like the IEC 60601-1 as we can. And because it has a switch, and because the device applied parts are isolated from protective earth, it should be the direct method. Now, differential could be chosen, that's okay. Even 60601-1 would still be okay. Remember, the only reason that we do not choose 60601-1 is because there are tests within it that will shorten the useful life of the medical device. Therefore, we don't want to use it for routine electrical safety testing, which is why the 62353 exists anyway. For those of you that pick differential, I'm not going to say you're wrong. I'm just going to say there are good reasons here why we would have picked direct, given this scenario. So what are those? The device has an accessible ground and three connections on the power cord. It has a switch, so it should never be alternative, never, because it has a switch. And it includes isolated applied parts, therefore we would pick direct. That's our rationale. Okay, and you can add questions about that if you choose, but I've tried to answer them for you already. Good job. All right. So there's a little bit more to know here, and this is a little bit more difficult. This has to do with those kinds of medical devices that are permanently connected to mains. And I think that that's the subject of another webinar that we have that I think I would prefer to spend more time on. The patient monitors are not those kinds of medical devices. They are always have a power cord and plug into mains power in the wall. So I'm not going to spend a lot of time on this part of the testing. But there are some more things that, based on what is the power supply coming that's being used to deliver the power to that mains connection. And you can see here that if there's electronic switch and it is a permanently connected to mains device, there are different choices that we would make about direct, alternative, or differential testing methods. Now, I'm not going to spend a lot of time explaining this right now. It's explained better in a different webinar that we have. So before we shift to the more specific slide deck about patient monitor testing, let's just review what we've learned. The IEC 62353 recommends measuring applied parts leakage currents by the application of mains voltage to the patient connections and having those connections all short-circuited by function. So ECG leads, we really mean by function, we mean applied part type. So applied parts like temperature sensors, thermistors that connect to the patient's skin, those are B type, those are grounded. And so we would test those with 100% of mains voltage applied when we do the test. Now you may remember under 60601-1, we use 110% of mains. But under IEC 62353, we just use the mains voltage on these patient connections. If they are an F type, meaning BF or CF applied parts, we just need to group those all together by type. So that would be all ECG leads and the invasive blood pressure leads shorted together and tested with 100% of mains power to test the isolation barrier that it protects the patient. That's what that test is for. That is the isolation test, okay? So 62353 recommends that we do the measurements the way I've just described. Both the power supply circuit and any ground connections are not removed and have no effect on the result. The test is only is the only measurement to be performed on the devices with an internal power supply. Okay. All right. All right. Now I'm going to quickly change decks. So I will temporarily stop sharing and then come back to sharing. Bear with me for a minute. Bear with me for a minute. All right. Now, I hope, Dan, we're seeing just the slide
Perfect.
itself. Yeah. Okay.
Yes.
All right. So now we're going to talk about doing electrical safety testing on patient monitors. And actually, this comes from the Medical Device Quality Assurance course series. The
Excuse me,
one
Jerry,
that,
if you could slide your GoToWebinar window. There you go. Perfect. Thank you.
okay. This comes from our MDQA course series, and we're focusing on the entire test for patient monitors, but we're going to try and focus only on really the electrical safety part of it. Remember, there's a lot more testing that needs to be done on the patient monitor besides just electrical safety testing, but our focus today is about just the electrical safety tests and nothing else. So it is true that the patient monitor includes electrodes and catheters and transducers that connect to the patient, some of which are continuously conductive all the way from the patient monitor to where they touch the patient, and others of them that are not continuously conductive and still provide information, like cuff blood pressure, NIBP, okay, for example. There's no electrical connection there, so for electrical safety, we don't care. So we do have a risk assessment for determining how often we should do the patient monitor testing that is included in this particular course about testing patient monitors. And there are 5 criteria that we use when we make that decision. Again, this is a decision that is made when we first do incoming inspection or acceptance testing of any medical device. We make the decision about how often we're going to test it. The manufacturer should provide that information to us in the brand and model specific service manual in the test procedure there. But a lot of times, especially in India and other parts of the world away from the US and Western Europe, the manufacturer does not provide that service manual or even the test procedure to you. And so you have to have some way to decide how often the testing ought to be done. This is the way that you do it. And again, I'm not going to go into this in great detail here, other than to show you the total risk score that is obtained using this worksheet is 10. Any test that is 13 or higher would be twice per year. Well, this is not even 13, it's only 10. So a overall risk score between 9 and 12 would be tested once per year. And so we are 10, therefore that's the applicable one. So the testing that we would do, how often we would test patient monitors, should be every year, once per year. Now, keep in mind, this is how often we're going to do our scheduled testing. We still will do the incoming inspection testing, all right? In addition to that, we will still test the patient monitor after any repair, right? So let's roll back for a minute and let's say, what if I had to send the patient monitor away from the hospital biomed department for that repair? Well, then it's going to come back into the hospital and we will do an incoming inspection. So we'll have that electrical safety test after we receive it back from whoever repaired it for us. We should do another electrical safety test. If we do the repair, then we must test after the repair to be sure that we made this patient monitor safe for the patient to be connected to it. You opened the patient monitor up and you replaced something. Therefore, you have to guarantee that it is safe for use. And think about it this way. How do you want the patient monitor to work if you or somebody you love is the next patient connected to it? Just answer that one, because you don't even have to have any government enforced standard to tell you the answer to that question. If that answer to that question is not, I absolutely would test it, then think again and think with your heart and then use your mind, because it needs to be tested after every repair, and it needs to be tested when it first comes into the hospital, and it needs to be tested once per year to make sure that it continues to be safe and effective for clinical use. So once per year is how often. All right, so how long should it take? Well, a 62353 direct method should not take more than 15 minutes to do the whole test. And in fact, it shouldn't take more than about 5 minutes to do the full electrical safety test on a patient monitor. What kind of test equipment would we expect to need for the full patient monitor test? An electrical safety analyzer, a good patient simulator. You still will need a stopwatch with this, or a watch with a second hand, and you'll need tubings and connectors appropriate for connecting to the patient monitor, and a cuff mandrel or something appropriate to wrap the blood pressure cuff around for NIBP testing. If the patient monitor includes any end tidal CO2 or multiple gas monitor function, you need the appropriate certified test gases to make sure that that function is properly responding to the patient's exhaled gases. Right now, we're going to focus only on the electrical safety. We still will check the physical condition, because we need to look at the patient patient monitor power cord and look at those mains power connection points. Make sure that they are not damaged. Make sure there's no frayed insulation jackets around the power cord and the lead wires. There's no dry rot or cracks or anything. So all of those things need to be evaluated. So I'm including those along with the things that should be done for any electrical safety test. And finally, we come to the electrical safety part of the testing. We will measure the ground wire resistance and the leakage current to ground. We will measure what is called chassis leakage in the 62353 and the IEC 60601-1 3rd edition. Chassis leakage is now called touch current. And the reason it's called that is because it is the current that could flow to the patient if the patient were to touch the medical device, or if the nurse or the doctor were to touch the medical device and be touching the patient at the same time. That's called touch current for good reasons. You're touching the patient. And by the way, you can demonstrate this very easily by having a patient monitor and touching the patient monitor while you are holding the test lead for chassis leakage. And in fact, if you have a buddy, you can have them touch the monitor and then touch you while you're making this measurement, and you will see that current is flowing. That's because you, the patient, and the caregivers are all electrically conductive. We are not insulators. We are all conductive organisms. So touch current, formerly called, before called chassis leakage, is a measurement that we will make. And as a matter of fact, that is the test, the one test in electrical safety that must always be done, no matter what. You can and should do that touch current leakage test. And then we will do the patient leakage current test. That is the patient applied parts leakage current. Those patient connections that are continuously conductive from the medical device, the patient monitor in this case, all the way to where they actually touch or go into the patient. And the mains on applied part test with 100% of mains power applied to each patient applied part type grouping altogether. Okay, those are the tests that will be done. All right, another poll question here. Which of the following F-type patient applied parts must be tested for electrical leakage? And select all that apply in this case, all that apply. So that means you may have more than one answer, right? And Dan, I hope that we were able to set this one up. If we weren't, that's okay. We'll still give them a little time. If you weren't able to set it up, then I recommend everybody respond in the question section.
Yeah, I'll go ahead and launch the poll here. It is just select one. So if you have a second one, if you want to answer that in the chat, there you go. Yeah, we're getting some folks in the questions answering.
Good, very good.
So I'll give you guys a few seconds to do this one. So in the questions, we got a lot of A and Ds, A and D. A, C, and D, A, B, and D. All right, I'm going to go ahead and close the poll. And share it. So 77% ECG, and then the rest of them are kind of split on which one would be the other option there. So I'll go ahead and hide this.
Okay, here's the big reveal. The appropriate answer, again, this is our point of view, the appropriate answer should be A for sure, and B, the invasive blood pressure leads. NIBP is tubing and a cuff. There is no electrically conductive part of this going to where it touches the patient, none. Therefore, nobody should have answered C. And pulse oximetry, SpO2, has been questions. It's a little controversial, meaning there are people that think it should be and other people that think it should not be. Here's our point of view about SpO2. SpO2 touches the patient with a durable sensor, finger clip or ear clip, or a disposable, single patient use disposable sensor that could go on the finger, it could go on the forehead, or it could go on the ear. On babies, it goes around the thick part of their foot, typically, to make pulse oximetry measurements. And where it touches the patient is not electrically conductive, really. It's not conducting electrical current to the patient. It is a light source. It is an LED, pair of LEDs, red and infrared LEDs. In Masimo rainbow pulsed co-oximetry, it's still just a couple of LEDs, but they're using 7 wavelengths of light, okay? It is not continuously electrically conductive to where it touches the patient. Therefore, we say there's no reason to test it. Invasive blood pressure is a little different because there are still parts of the world where the invasive blood pressure transducer is reusable. So you might have a controversy there if it is a disposable transducer and you never reuse it on a second patient, and therefore only the lead wire that goes to that invasive blood pressure transducer would be continuously electrically conductive. I am open to discussion around whether B is appropriate or not appropriate. However, our point of view right now is ECG leads for sure, and probably invasive blood pressure, because that invasive blood pressure catheter goes inside the patient. It breaks through the external skin and goes into a blood vessel or into the heart itself for cardiac output catheters and things like that. So, ergo, these are the reasons why we say IBP probably needs to be tested. Temperature should be tested, but it's not an F-type applied part. Temperature is typically reference to ground, not to isolation, okay? So there's no isolation barrier there to test. Okay, here is the worksheet that is used by, that is presented in our MDQA electrical safety book chapter and course. And it includes the physical inspection up here at the top, and it includes the electrical safety tests that need to be done by patient applied part type. You see this? And it includes the leakage currents. This is not the test procedure. This is the worksheet that you fill in to report your test results. And for those of you who think that the worksheet is the test procedure, that's not correct. So in the book chapter, the chapter itself is the procedure, and this is simply the worksheet that you're going to fill in to report your results. If you have this already in some other automated workflow in your computerized maintenance management system, that's fine. But you have to have some place to report your results, and this is what we're showing you here. Okay, who tested it? What date was the testing done? And some information about what exactly is the patient monitor that we tested, including its serial number and its hospital control, inventory control number. Okay, so these are the tests that would need to be included, and they come directly from the IEC 62353 direct method test procedure. All right, so we're back to the lead isolation tests, the F-type applied parts tests, and the question in that decision tree from the 62353, if there are no F-type applied parts, the answer is no here, then we just document the leakage current tests that were done before this. If there are, then we have to do the applied part tests, okay, for whichever method that we're using. Okay, just so you can see how that bottom part of the work of the decision tree works, and documenting the results. In this case, we would do that in the worksheet. So let's have a little closer look at what that part of the worksheet includes. So applied parts under IEC 62353 need to be tested for F-type applied parts, that is BF or CF. These are isolated from ground, all right? The B-type applied part, like temperature sensors, are referenced to ground. So we can see what the allowable leakage currents here are, and we would enter our results over here for what our measurements are, compare them against the maximum leakage currents allowed under the standard, and get a pass or a fail. Okay. So, and you'll notice they're here by whichever of the test methods we have chosen for this category of medical device. So patient monitors are direct, so we wouldn't fill anything in here. We would fill all our information here under direct or differential method. Okay. So our maximum leakage current for chassis leakage and leakage to ground is 500 milliampere. Our applied part leakage for direct method for the patient connections would be 5 milliamps or 100 microamps, depending on whether it's a BF or a CF. Insulation testing, which is the quality of the insulators wrapping around the conductors in the power cord, that quality is being done at 500 volts DC and gives us a measurement in the megohms range. And if we have to do that test, which is not required unless the manufacturer requires it or your local national electrical safety standard requires it. Otherwise, it's not, you don't have to do it. If you do it, your expected results should be more than, not less than, more than 2 megohms, more than. We want a very high resistance to any current flow from one conductor to another conductor inside that insulation jacket. That's what that means. Okay. All right. We've completed our introduction to patient monitoring testing. So now what I'm going to do is end my slideshow and come back to so I've ended my slideshow and I believe that it's time for Ravi and the group to pick up where we have left off.
Good evening, everybody. Let us start to have a live demonstration about electrical safety testing on patient monitor. Here we are using a patient monitor and IEC 615, and let us go the test at what we have learned one by one. Let us start this one. If anybody is having a difficulties or you wanted to understand something, please write back to me at info.india@flukebiomedical.com, or you can write to ravi.ma@fluke.com. Okay, let us start this one. Yeah, now actually first we start the testing. First we try put it on we put on the equipment. You can see if there is no problem with the ground or L1, L2 reversible, it will directly come to the display. It is showing like this. Able to see? Everybody is able to see? Okay.
Slightly
There will not
focus.
be. Yes.
And Ravi, if you want to stop sharing your screen, just the video is all we need to see right now. Oop. You're sharing your screen, right? Rather than sharing screen, just turn off your screen sharing and share your video.
Shall I? You are going to share the video? Hello.
You can share the video, Ravi. You are able to share the video?
I am sharing the video.
Perfect. There we go.
Yeah.
Okay.
Perfect.
Now you are able
Thank
to
you.
see.
Yeah. Fine.
Okay. First we do the ground wire resistance. Put on the equipment. Okay.
Ravi,
First,
can you,
actually, before.
Ravi,
Yeah.
this is Jerry.
Yeah.
Can you please comment on how you make sure that you are testing to the correct electrical safety
Okay.
standard?
I mean, BF type or CF type.
No. Which electrical safety standard has been
We are,
selected?
we are
Direct
going to. We have selected IEC 62353. Okay. We are doing 62353, and then ground fault resistance is at 10 milliamps. We are doing, it's a 62353 test, not 60601. You are able to see the screen of the 615?
It's difficult to
Are you
see
able
the
to
screen,
see?
Ravi. Just read what's on the screen because you have too much glare and it's not going to really, you're not going to be able to really see it.
Okay.
Yeah, maybe background light if you can switch off one of the lights.
You know what? I just read what's on the screen because
That's fine.
it will take too long to try and work out the removing the glare. Now, see, that doesn't help either. No. Just read what's on the screen so we can understand. And everyone, this is difficult. It always is difficult. So we will show you the big parts of how you got to move your test lead and all of that and read what's on the screen. And then at the appropriate time, you can all ask for a demonstration of this at your facility one way or another. And that you will contact the India team, please, from Fluke Biomedical, and we can arrange for that to happen. For right now, just go along with us so that we can move on and not take more than the amount of time that we promised you.
Fine. You can go ahead, Ravi. You can read it out. It's fine. Yeah.
We are actually set the test thing as 62353, and we are going to start the measurement with ground wire resistance. And before doing the ground wire resistance, we need to first do the leads zeroing, because you will be aware what we are using the leads which are having a resistance freely built in. So we have to zero the leads first before doing a ground wire resistance. Let me put, there is a null post available on the equipment. We are going to put it on that, and then press, there is a F4 button. You have to press 0 to do the test. You will be able to see that it is showing 00 ohms right now. Okay, you are able to see, I believe. Okay,
yes,
then yes, we take that red wire and then put it to the ground wire jack on the back side of the monitor. Everybody is able to see? We are going to put it on the ground wire jack. You are able to see the resistors?
Yes, visible.
Okay. This is the first test we are going to do. Record the readings. Next, go to chassis leakage. For doing the chassis leakage, you have to press microamps. There is a microamp switch is available. You can do the test using direct method, differential method, or alternative method, as we have understood in the previous this presentation. We are going to do it on a direct method. Okay. Now see the reading which is coming 1. We can test actually other than that we can do by doing AC or only by AC or AC plus DC or only DC. We can do all these things test, and then next is actually we can do a faulty condition, single fault conditions. We can test it. For doing a single fault condition, we have to test the press polarity. There is a normal polarity. You are going to see 2 microamps. It is showing. And different equipment may show different readings, but this is which is what it is showing. Now, actually, I am going to open the ground, which is single fault condition. See, normal condition it was showing 2 microamps. Now on the single fault condition it is 4.2 microamps. I can do other way of this one single fault condition by reversing the polarity also. I am reversing the polarity is L1 becomes L2, L2 becomes L1. This is the reverse polarity. Reverse polarity is also showing the same thing. Next, I am just showing even the differential methods. If anybody is interested, you can see what is the difference it is showing, what is the current it is showing. Here also we can do normal polarity, reverse polarity, and then closed ground or open ground. Okay, test. Now actually I am doing mains and applied parts. How to do the mains and applied parts is just press a mega ohm button. You are able to see this actually. You can press it and then do the testing. Please be aware whenever you are going to do the testing.
Sorry, Ravi.
Yeah.
Megohms is for the insulation test only. That is 500 DC or 250 DC.
Okay.
That is not the mains on applied part. Mains on applied part is done under the leakage current test, under microamperes, and there should be a mains on applied part test under that setting, and probably it's the more button to get to it.
Yes. Okay. Now alternate we are doing, and then we are going to test it, applying the voltage and testing the alternate equipment leakage. This is showing 165.7 microamps, which is okay, fine, we can accept. Now we are doing the direct method on the applied parts. You can do the testing plus test. You can see the reading, and then we can do even alternative applied parts also. Then press test. This is the reading what we are going to get, or it may differ. On this equipment, it is showing like this. Next test. We are going to do the insulation resistance test. Now we are going to do mains to protective earth. You are able to see, I believe. Then press test. Please be understood that OL is not the for the resistance. If it is showing OL, it's acceptable because it is more than the required resistance. Okay. Now applied parts to protective earth. I am just doing the applied part to protective earth. You can see 98.5 mega ohms. Anything above 3 mega ohm will be acceptable. Okay, next. Next is mains on applied parts. Mains on applied parts is acceptable because it is having a very good this one. And then another one thing I wanted to tell you, you can change the voltage to 500 or 250. Okay. And next test, now actually I have done it on the protective earth. Now I am going to test it on the neutral. This is fine. And applied parts to neutral. It's acceptable. These are all the tests we have to do, and the electrical safety is that's all for monitor testing. Okay. Okay, Jerry, anything else you wanted to show? Hello, Jerry.
No, I'm here. No, unless so I think, Dan, we're ready for Q&A, right?
Yes.
Sounds good. And I've been chatting with one of our other partners here that is collecting the questions, and we'll go ahead and get started. We have quite a few questions coming in, so
That's good.
Yeah.
Touch current.
Yeah, Ravi, you are saying something. Go ahead.
Jerry, I wanted to tell a little bit more on the touch current on a plastic body. How to do a test current on a plastic body. I wanted to hear from you, and everybody wanted to hear.
No, please do. So describe, Ravi, where the test point is. What is the test point for touch current?
Test point on a plastic body. How we are going to do the test touch current test. Finding out a touch current, chassis leakage. Jerry.
So the standard describes for us that we should use for the touch current test a conductive but non-earthed, non-grounded test point where on the medical device where the patient would be likely to touch it or the caregiver would be likely to touch it. Well, here's the little bit of a problem. On an awful lot of the medical devices today, including patient monitors, do not have any conductive test point where the patient could touch it. There just aren't any, earthed or not earthed, grounded or not grounded. So the standard says we use a 10 centimeter square of aluminum foil. And so you might have to use 2 or 3 layers of aluminum foil, but in a 10-inch square, and you are to tape that onto the touchable surface of the patient monitor. Just tape it down, make sure it's in close contact with the medical device, and then you clip your test lead to the aluminum foil. And the reason that we do it that way is it's a test that must be done. And remember that we are all humans conductors. So if the patient, there's electrical current conductors inside the medical device, and the plastic covering is an insulator. Yeah. So if a human being touches the outside of the plastic, we form an electrical component because we are a conductor. So we have a conductor, an insulator, and a conductor. For those of you who have taken electronics courses already, you know the component, the electronic component that describes conductor, insulator, conductor is called a capacitor. And that's exactly what happens. The current flows by being capacitively coupled from the inside of the device to the outside. And so if the patient touches it, the current will flow through the patient to its reference. Okay, so we're going to create that condition by using the aluminum foil as our patient or our caregiver. And we're going to clip our test lead on there to measure the current that could flow if the patient or the caregiver touches the medical device. And that's what we're going to do. And Ravi, I don't know if you're prepared with aluminum foil or not today, but
No.
I have described what to do.
Yeah, actually, this is what actually we are going to show it tomorrow. Those who have attended today can join tomorrow again. We will show this one aluminum foil test, how we are going to do it. This is what the next tomorrow's session, and please come back with your questions anymore, and you can write back to us also. We are going to do it the same aluminum foil test tomorrow morning, tomorrow session.
Okay. And this, as I said, this touch current leakage test and the way we have just described it is for all medical devices. It's not just patient monitors only, all. So anything that we have where we have no conductive test point, we will use the aluminum foil for the touch current, or formerly before called chassis leakage test.
Okay, then I think we will go to the Q&A quickly, Jerry. There are some, yeah. So, okay, gentlemen. So thank you for your joining today's session. So then I have tomorrow also we are starting the session at the same time, right? At 6:30 p.m. Same time,
Yes.
right?
Yes.
Okay. So before we start the Q&A, again, reminder for all who has joined today and whoever has registered, your friend or colleague who have registered for tomorrow, kindly note that tomorrow we are going to start at the same time, that is 6:30 p.m. 6:30 p.m. Indian time. So please make a note of that. So, okay, Jerry, first question that has come in is, I think it's very, you have covered it during the first few slides. What is called, or what is earth-bound test?
The what? Say
What is
again.
earth-bound test?
Earth bond. Earth
Yeah.
bond is the same, is a different set, different words to describe what is the ground resistance or earth resistance or protective earth resistance test. That is the ground bond test.
So It's
Same.
basically the same name. Earth bond is like protective earth test.
Correct. It's a very
different name.
fancy, formal way of describing it that is used in the standards, the electrical safety standards, but it means that protective earth or ground wire resistance test.
Great. Thank you for clarifying. So next is okay. I think how is the device power and leakage measured? I'm not sure whether the question is clear. How is the device, duty, power, and the leakage current measured? So it's a, little open-ended question, I think.
Well, yeah, very open-ended, and we showed how it's done. You saw with your own eyes how it was done.
Exactly. So it's basically come once you start using the machine, and we have shown Ravi has just demonstrated how it is done. So probably you can get in touch with us again if you want to have further demonstrations. We'll try to see how to arrange it. So next question is, what do you mean by F type? I mean, that is cleared. It's either CF type or BF type.
Correct.
So yeah. So because Jerry has mentioned about F type, because F type the type where we need to have the applied parts testing, right, Jerry?
Correct. That's correct.
Yeah. So F type is for F is basically generalized it for CF type or BF type.
And just remember that the two different F type applied parts, BF and CF, each have their own leakage current maximum limits. Okay, each have their own. So you've seen that in the worksheet. We showed you that. So and if you want more information about that, you can go and take the advanced training course, MDQA, Medical Device Quality Assurance course series, especially the one around electrical safety, and we go through that again. And there are other webinars and videos where we go into that detail again. So the course allows you to download and print out, if you want to, the chapter, the book chapter. So you have access to everything you need in order to understand it.
Okay, next query is the next question is that do you advise the applied parts test? Yeah, that is, that you have already informed. In any way, I'll just read it out the question. Do you advise the applied parts testing, I think, during IEC 62353? Yeah, it's definitely.
Yes, it's required if there are continuously conductive patient connections. Yes, it's required. It's not do we recommend it. The standards require that it be done. And if you have the manufacturer's service manual test procedure, they also require that it be done. So you must do it. To avoid doing it means you have not completely tested the patient monitor, and your patient may have a higher risk of being injured because you didn't do the test. So once again, how do you want the medical device to work if you or somebody you love gets connected to it next? Have to do.
It's true. Okay, next question is that why does some of the electrical testing analyzers are suitable for clinical medical device but not for research use medical device? So
For not
do you want me to?
for
Okay, I'll
not
repeat
for
the
what?
question.
Yeah, please.
Yeah, why some of the electrical test analyzers are suitable for clinical medical device but not for research use medical device? Probably some more clarity on 60601 and 62353.
Well, so in order to be fully compliant with the IEC 60601-1, which is the most complete requirements, you need to be able to do 25 ampere protective earth resistance testing, earth bond resistance testing, and you must be able to do 110% of mains power on applied parts. So you can do tests that are similar to 60601-1, but they can't do exact compliance to those tests. So if that's what you need to do, if you are working for a medical device manufacturer in the production line or in final assembly, I'm sorry, in design validation testing, then ESA 615 is not the appropriate test instrument. You would use the ESA 620. And by the way, in those situations, you are at a bench. You are not moving around the hospital or from one location to another location for clinics or like that. So you don't need the same portability that you need that where you're going to use the ESA 615. And by the way, the portability is important, and the fact that 62353 is a test standard specifically to help us do our testing after we first receive the medical device, whether it's in a clinic or a hospital or another location for another part of the hospital. That's exactly why they're there. All right. So the requirements about which test instrument you would buy depends on what is your need exactly. And our India team can help you with that.
Yeah, thank you very much for clarifying this. And the next question is like, why sometimes when start electrical safety EST testing, basically the ground wire resistance test does not pass until takes time, basically. That's what does that mean that I must replace the power cord?
Sometimes it means that.
Yeah.
Right. So sometimes it means that. Sometimes it means that the power cord plug, the part that you plug into mains power or you plug into the test instrument, that plug end, the connections have become loose or broken, and you have to replace that power plug. If that's the case, that is, it failed the test, you will do a repair called replace the power cord or replace the power cord plug itself, wire it properly, and then repeat the test so that it passes, and then continue with the rest of your electrical safety test.
Okay, so next query is that what do you do to rectify tests that records values out of expected range?
You have to troubleshoot to find out why.
Yeah,
You have
that's
to
true.
find the root cause, fix it, and then repeat the tests.
So basically what you are saying is that it indicates there is some hardware or something else needs to be checked in the medical device.
Something we can't
Yes.
tell because it'll be something different every time. So
That's true.
you're being paid to understand medical electronic equipment and be able to troubleshoot it. And if you cannot, there should be somebody in your department who can, or if you have no one in your department that is capable of that, then it's time to get the manufacturer's service engineer to pay a visit or to send it out for repair. But not ever put a failed medical device back into clinical use. Once again, how do you want that patient monitor or medical device to work if you or someone you love is the next patient that'll be connected to it? Would you do that? No, you would not. So don't. You have to repair it first.
Okay, so next question, I think we covered it during our last webinar. So, but I think it's a basic question. I'll just go about this. Is it necessary to switch on device during testing? I mean, that's a very basic question, but you can clarify.
So today we're talking about IEC 62353 compliant electrical safety testing. And under some, like the alternative method, that testing is done only with power off, period. Only with power off. But you could see in what you learned today that decision tree shows us there are only a few situations where the alternative method is the right method to use. Otherwise, in differential or direct method, we will do power on and power off, normal condition, normal polarity, and reverse polarity when we do our tests. And we will do single fault test conditions also. The whole purpose of electrical safety is to find out the answers to what if this or that, and how much current is flowing, and where is it flowing, in what conductor, down what return path to its reference is it flowing. All right. So
Yes.
those are the questions that we need to answer when we're doing the testing. Only the alternative method would only allow us to do the testing with power off only. All the other times it is both power on and power off.
Okay, so this question you can quickly just answer. I think this also we covered last time. How about EST for battery operated device?
So battery operated devices, what is the return point for a battery? The opposite pole of the battery, yes? We are actually not allowed to open the medical device or its battery in order to get to the reference point, and therefore we need to do that test in a different way. We would do a chassis current test for sure, but the battery powered device is designed to work off its battery only. If it has a connection for mains power, it is only to recharge the battery and typically not to run the device from mains power. In any case, we are testing an IP, a class IP internal power device with its power coming from its battery only. Now, what would we use then? Well, we have no place to plug in the device, no way to plug in the device. So we would use a test mode on the electrical safety analyzer called point-to-point testing, and it allows us to do the well, there's no ground wire leakage there to worry about, but we can do the current measurement and do the touch current or chassis leakage current measurement using point-to-point testing. And we would do it the same way as we've just described, either to a conductive test point on the outside of the medical device, or else put the aluminum foil, clip our test lead to the aluminum foil and make the measurement that way.
Okay, so thank you, Jerry. Next question is, okay, very basic question. Which standard shall a hospital engineer should use? Is it IEC 60601? I mean, you have already clarified. So if,
Yes, I'll remind everybody that
Yeah.
the IEC 62353, if your country has adopted it and allows it, is what is the standard that should be used by hospital biomedical engineers, independent service organization, third-party service providers, their field service engineers, and the manufacturer's own field service engineers. They should all be using IEC 62353.
Yeah. Next question is, why the leakage current is not isolated by the isolation circuit?
Leakage current is going to flow no matter whether there's isolation, no matter whether there's ground or no ground. Leakage current will flow. You have to know how much, where is it flowing and how much is flowing. So you have to measure it in order to do that. There will always be leakage current. Even with power off, there is never a situation where no current will flow. There will always be a current, and you must measure it, you must document it, and identify for pass or fail according to the test limits in the standard.
Okay. Which method is very accurate for measuring leakage current, direct or differential? I think it's already clarified.
I already have said that many times during this presentation, right?
Yeah. We can go to the next query. What would we define electrical safety testing? Is it a calibration or test verification?
You are making a measurement on a medical device. It is by definition a calibration. By definition. So remove from your mind, please, the idea that a calibration includes an adjustment. It does not. The adjustment to bring it back into tolerance would be a corrective action, a repair. So you are evaluating parameters that are required by the standard or by the manufacturer's service procedure, testing procedure, to document and keep track of the condition of that medical device. It is, therefore, a calibration.
Okay, I'll quickly go to the next question. Is that how about how can you check the earth resistance for a three-phase, or how can you ensure that the earth system is connected to the machine in the three-phase by digital multimeter?
All
I'm
right,
not
guess
sure.
what? There is no multimeter that tests all three
Yeah,
phases at the
exactly.
same time, my friends. There is none.
It's
Get
true.
that out of your
Yeah,
mind. That is not the right question.
possible. Yep.
The three-phase power supply delivers power in one or another of each of the three phases to a set of circuits or portions of a room or a system separately. So when you do testing where the power has come in three phases, it's being broken out already for what you think that you're going to test. You're not really testing three phases. You're testing leakage current only for the phase that is being used to power that part of the system or that part of the room. Period. That's all. You are not testing that three-phase power supply for leakage current tests. You're not doing that. Okay. So take that out of your mind. And that means that you must be able to get on the appropriate reference, whatever the phase is. Most of the time, you are not allowed to break into the power supply or the mains power source in order to make that measurement. Okay, so that means that you need to use point-to-point testing and understand how to do that. Now, there are certain circumstances where the manufacturer of a medical device, like an X-ray system, an X-ray room, provide a opening in the electrical panel for you to get on the correct reference point for the phase of the power that is being used for the part of that system or that room that is important to be tested. You follow the manufacturer's instructions exactly when you're doing that. And you never just do it out of your own mind or what you think is right, okay? There is no such thing as testing all three phases leakage current. Not. We don't do that.
Okay, thank you, Jerry. Next question, we have a few more left out. Even after doing electrical safety testing, if the instrument falls above a score of 12, is it advisable to use it? So basically, he's
No,
referring to
so,
the,
all right,
yeah,
so you're being confused. The question about whether the total risk score is whatever it is has to do only with answering the question, how often shall I test electrical safety, or how often shall I test performance of this medical device? It's just how often. It's not about whether it passes or fails. It's about how often shall I test. For a patient monitor, our total risk score was 10. That is between 9 and 12. That means one time per year. We will test one time per year. When we test, we will follow the IEC 62353 appropriate testing method and carry out the electrical leakage part of the safety and performance testing that needs to be done. I hope that makes it clear.
yes. And one last question, Jerry, like what about patient monitor connected to a central monitoring system? Should the EST be done, performed on a central monitor also?
No, so there is a test that is often referred to, and again, people are all confused about it, called SIP-SOP, meaning signal in, signal out. It is a test that is only done by the manufacturer during final assembly testing and design validation. It might be done as part of an installation of a patient monitoring system connected to a central monitoring station. But aside from that, it is not a routine test that you're going to do even once per year. Not. And there's a special way of doing that testing. We have a separate application note that explains how that is done if you want to know, but it's not a test that you're going to run routinely, nor should you.
Thanks, Jerry. Thanks for clarifying. I think we have answered most of the questions, but if any of the attendees feel that they have query, please mail it to us, and we'll definitely get back to you. You can either mail to tech services at techservices@flukebiomedical.com, or you can reach out to India team also, info.india@flukebiomedical.com. So thank you, Jerry, for being, taking us through this journey. And then tomorrow, as I said, like we'll have the same session. We'll start it at the same 6:30 p.m. sharp. Please note, we'll start 6:30 p.m. sharp. So looking forward to your joining and valuable learning for all of us. Thank you very much. With that, we'll be closing it for today.